You can go ahead. Thanks.
Okay, so we have this weirdly scheduled pizza seminar without pizza, unfortunately. So today's seminar, we should have give the seminar on Friday, but as you know, in the next few days there will be an electricity cut-off, so we cannot have our activities. And today's speaker is Sujay Mate. He is a postdoc now at the Tata Institute of Research in Mumbai. He got his PhD in Toulouse at the IRA in 2020, right? 21. And he's an observer and the instrument astronomy, has been working with SBOM and now with Daksha and other things that he will tell us about. Yes. So go ahead.
Thanks, Alessio, and thank you all for hosting me. So I'll talk about some instrumentation work which we are doing in India related to detecting X-ray and gamma ray transients, also X-ray gamma ray transients and radio transients in millisecond related like timescales. So the overall science theme is that like we have now these energetic explosions involving compact objects like gravitational wave events, gamma ray burst, and fast radio burst. So one of the key questions currently is that are they related in any way? Like, do we have like are there some populations which are counterparts of each other? So, for example, we know for sure that short GRBs are related to gamma ray burst. Short GRBs are related to merging neutron stars, like binary neutron stars, and we had a conclusive proof about 6 years ago. Then we also know in some cases, at least FRBs produce gamma ray flares, which was observed in 2020 with these HGR magnetar, the galactic magnetar. And then there are theories, for example, that some gravitational wave events involving neutron star could produce FRB-like emissions. So to basically address this problem, we need to have instruments working in both the very high energies as well as at radios, and they also should be sensitive at these timescales. So I'll first start with the high energy part, where I will talk about this proposed mission called Daksha, which means to be alert in the local language. So it's a part of bunch of institutes involved, like astro institutes in India, including ISRO, and it's in the under proposal phase. So to give a science motivation, so before I go into details, I'll just quickly touch upon gamma ray burst if people in the audience are not really not familiar with exactly. So GRBs are basically very short duration gamma ray flares, which last from milliseconds to few hundreds of seconds, and these are the most energetic explosions in the universe. And they are typically have a broadband emission. So the typical scenario of GRB is shown here, which is what we have understood over the last about 50 years of studies, is that it involves a central engine which launches a relativistic jet, and this jet, even the emission from within the jet is called a prompt emission, and that is what is observed as the gamma ray flash of few seconds, a few milliseconds. And then as it jet collides with the surrounding medium, it slows down and it emits something called afterglow, which is observed in all the wavelengths, ranging from even high energy all the way down to radio. And typically right now, GRBs are classified into short hard GRBs, which are about less than 2 seconds long, soft, which are about more than 2 seconds. But now we have recent observations whether these definitions are also getting in question nowadays. And as I said, we have one conclusive proof that they are multi-messengers in nature, that BNS merger produce short GRBs, which we have observed. So quickly, like why are they important on the astrophysics part of view? That of course the first question is that they are very energetic. So they are the jet itself is at a very high energy and density. So we want to probe the physics. And since they are also at a very large distances, and then the jet interacts with the host galaxy and even surrounding medium, so they are very good at probing the host galaxy or tracing star formation, and also do some cosmology. Although we have had studies we have been detecting GRBs since 1960s, 70s. We don't really understand many of their properties. So one of the key questions still which we have not able to address is that what is the exact emission mechanism behind the GRB jet, and the geometry, like what or also the composition, like if it's a matter or a baryon or a Poynting flux or a magnetic field dominated, and questions like what are the true GRB rates, because and then their redshift distribution, for example, because we only observe GRBs if the jet is pointed towards us. So we also don't really have a good constraint on that. Yeah, and on top of that, as I said, we have a proof of short GRBs being counterparts to the binary neutron star mergers, but the one event which we detected have also opened many questions rather than solving our understanding that okay, they are the same population. That the one which was observed was typically faint compared given the short GRB distribution which we have observed. So now that has opened, like if there is a new class of short GRBs which is associated with the binary neutron star mergers. And even when detecting this event, we were extremely lucky that the Fermi GBM was able to detect, because the LIGO localization, as we know, is not that great. And because Fermi was able to detect it, we were able to narrow it down, and then the optical telescope could follow. This is also because the flux of this, the fluence of the GRB was pretty low. And if you see the distribution here, this stands here compared to the other short GRBs which we have detected. So now looking at what has happened after that, it's been 6 years. There was one complete O3 run which had 11 events, which had a neutron star counterpart. And there is O4 happening now, and then also there is O5 which will come, and we have still not detected any another event like 17 or 70, and that means that we are most likely lacking the sensitivity in the detecting these, like in terms of electromagnetic counterpart space. So what we need is basically this: is that we need an order of magnitude higher grasp, so that basically higher volumetric reach. We need a wide spectral band, because some of these events are also expected to have significant emission in the lower part of the energy compared to the classical short GRBs, and also continuous all-sky coverage, so that we are not missing out on the on the events on them, because we were not looking at that part of the sky. And if you see the current instrument which are sensitive enough, there are only two major instruments, right? I mean, there are other GRB instruments also, but the workhorse of this field is basically Fermi GBM and Swift telescope. And both of them are pretty reasonably sensitive, but then one of the things they lack is that the sky coverage is also pretty limited. And also, for example, Fermi is a little the broadband coverage also not down to very soft energy ranges. And in case of Swift, you also don't have a coverage below 15 keV to detect in terms of detecting these events. So, and the future also, there are not many missions planned. The one which is could be add to the field is the SWARM, which should launch next year, April or May is whatever. And so this does have a good coverage in terms of energy from 4 keV to up to 1 MeV, but again, it is the field of view is small, and we will not be looking at that part of the sky. There are some concept missions of lot of CubeSats. So the idea is to make a network of CubeSats roaming or in orbit around Earth, and then try to localize using the time of arrival differences. But these proposals are in very preliminary stages, and there are few. There will be, I think, Black Cat and Bus Cube and GRB Alpha, for example, are some of these pathfinders are there on the will be launched soon, but there are only 2 or 3 satellites. It's just a very technology demonstration stage at the moment. So coming back to this requirement, we have some part of discovered by different missions, but we don't have complete all the 3 checkboxes done. So that is where basically we want to fill, and that is where the Daksha comes in. So the idea is to have full sky coverage and broadband energy range, and also to have order of magnitude higher grasp. So I'll just now go through what the mission profile is and about what is the design of the satellite. So what you see here is the one single satellite of Daksha, and the idea is to have 2 of them on the opposite side of the Earth, and it will also have on board a real-time detection capabilities. So if an event is detected on board, so any transient will be detected on board using one of these medium energy detectors. So each satellite will have, if you see that design, it will have open detectors in this dome-shaped structure, where there will be 13 faces on this dome. And on each face, there will be 2 types of detectors: the low energy detectors, which are silicon drift diodes; the medium energy detectors, which are CZT, like cadmium zinc telluride detectors. And there will be 4 of them also, four ME packages will be also below the satellite bus to cover the other part of the sky. And there will be 4 high energy sodium iodide scintillators inside the dome. So then you get coverage from 1 kV to about 1 MeV. And typically we will be able to localize up to 10 degrees for a threshold level, so like 3 to 4 sigma level transient on board. And of course, this can be improved upon on the ground. If you want to know more about the instrument, you can scan this QR code, and the paper link will be there. We are in the process of, the papers are submitted. It should come out soon in experimental astronomy. So how does it compare with the other mission? So it will have order of, like, the key would be that to have a highest volumetric survey reach. So we're covering the largest volume among all the mission. We'll have sensitivity. If you see the Daksha medium energy detectors, will have a sensitivity like similar to Swiftback, but almost on the entire part of the sky. The low energy also will be reasonably have a good effective area and will cover again almost all entire part of the sky. And the high energy also is slightly sensitive, more sensitive than the Fermi GPM detectors. So the key science goals will be, as I had briefly mentioned, is the EMGW, that is electromagnetic counterparts to gravitational waves, and classical GRBs. So with respect to EMGW, we expect about detection rate of 2 to 9 times compared to Fermi. And the large error in the number is because depends upon which model you use for the jet or the emission jet for the GRB and this thing. So this paper is also under right now preparation, and this should come out to actually put exact details, numbers of this calculation, and how what is the sensitivity of detecting EMGW events with Daksha. So in terms of GRBs, yes, of course, we'll detect a lot of them, the classical GRBs, and that will enable us to do like fine time result studies, also some broadband spectroscopy, because we'll have 1 kV to 1 MeV resolution. And also we can do GRB polarization of prompt emission, and about which I will talk in a bit more detail, which we have been working on for about a year now. Apart from that, there will be, of course, other auxiliary science goals, like in terms of compact objects. Of course, we'll be able to detect magnetar flares, and we can do all sorts of science with that. On that part, we'll be able to look for fast radio bus counterparts if they exist, and also monitor known X-ray pulsars over a long time just by phase folding. The closer to Earth, also we can do some science, which is like we'll be very much sensitive to something called terrestrial gamma ray flashes, which is basically gamma ray emission from the lightning strikes which happen in the atmosphere. And it's a very interesting subject because we still don't know what it causes. And then we have detections by Fermi and some detectors like ASIM on ISS, but it's a very interesting science for atmospheric scientists. And then, of course, solar flare and other atmospheric phenomena. And we can also, there will be additional science about putting constraints on primordial black holes and novae and slow transits. So again, the science paper of Daksha is, if you want, you can scan this. It will be available on this archive link, and also under review currently. So now I'll come back to something specific, which I have been working for a year, which is like measuring GRB polarization with the Daksha mission. So first is that, like, why do we want to do polarimetry with, like, why do we want to measure polarization of GRBs? So last about 50 years, we have been only doing spectroscopic and timing studies, and this is in general too for X-ray astronomy in general, because the polarimetry has not evolved as a field, and it only recently that IXP has launched, and that has opened up this another dimension. And because with only spectroscopy and timing, there are like constraints that you cannot really break the degeneracies between the models, and many models predict similar mechanisms. So the polarization offers this another window into studying the physics, because then you can probe the magnetic field of the jet and other in general the emission region. And so that's where it comes in terms also in the GRB prompt emission case, that with the by measuring polarization, we can try to find what is the composition of the jet, like if it's matter dominated or magnetic field dominated, what is the exact mechanism, and also the geometry aligned with respect to the line of sight. So there are typically 4 mechanisms right now proposed for GRB polarization, and depending, so this table is a little complicated, but the take-home message here is that depending upon the model, the jet viewing angle, the opening angle, and the Lorentz factor of jet, every model predicts different kind of polarization degree. So it's just looking at one GRB, we are not going to, we cannot really say about what is whether like what kind of polarization is typically expected. So what we need is a statistical study of prompt emission GRB polarimetry, and this is where we lack badly because over the last 50 years we have only measured about 32 GRBs in terms of polarization. So and those measurements have come only recently, like 5 years, like within last 4 to 5 years. So the 2 key missions which have advanced the field in certain extent is the Polar one, which was on the Chinese space station, which detected 14 GRBs. The other one is the AstroSat CZTI, which have detected about 20. Measured the polarization. That's a better word, for 20 GRBs. And there were some other missions also which have detected previously, like Bressy-Batse and integral, but those measurements are a little bit more contentious. So basically, we have only about 40 GRBs measured out of more than measurement of polarimetry for 40 GRBs out of more than 5,000 GRBs. So we really lack there. So whatever efforts we can do to measure the polarization in going forward is going to help us and address this problem. So yeah, this is just one summary of most of all the GRBs till now. And if you see the polarization degree against and these are the number of all the GRBs, and it's consistent with low and with a large error bar. So even the measurements we are not yet there in terms of accuracy. We need to improve this upon our statistics and methods. So yeah, so this is where Daksha can help us in between. So it's not a polarimetry mission, but we can measure polarization and can at least contribute to the field. So before I can come up, what's the sensitivity of Daksha? I'll just explain how you will typically measure the gamma ray polarization in at X-rays and gamma rays. So the main principle is based on Compton scattering. So if you have a photon coming and getting scattered with an electron, it gets scattered perpendicular to the electric field vector of the photon. And if you keep some scattering element in the center and put detectors around that, you get this kind of modulation based on the polarization angle and the polarization degree of the incoming photons. So the amplitude of this modulation gives you the polarization degree, and in the phase, if you set it with respect to certain frame, you'll give you the polarization angle in the sky. So this is the basic principle which used to measure the hard X-ray and gamma ray polarization. Now we can apply this to the Daksha CZT detectors. So this CZT detector, which are basically cadmium zinc telluride detectors, are pixelated, and we have about 256 pixels in each detector module. And the advantage of the material is that the Compton scattering cross section in the about 100 to 400 keV range is dominant over the photoelectric absorption. So it's that there are a lot, as you go higher, the more and more Compton scattering interactions start to happen in the energy. So if you have the pixelated detector like this, you can always find a section of 3x3 block where you assume that this is your central pixel is a scatterer and the others are 8 detectors. So you get 8 azimuthal beams basically. And then if you shine a photon like that, your photons get scattered in the perpendicular direction, which then can give you this modulation in this plane. So if you have a polarized light, you will have something like that because more photons will get preferentially scattered in one direction. And if it's unpolarized, you get almost flat distribution because the probability of scattering in all direction is almost same. So this has been already tested, demonstrated on AstroSat CZTI. So as I mentioned, all the polarization measurements which have been done by CZTI using the similar principle. So we already know how to do this. And however, there are with Daksha, there are slight complications because if you have off-axis incidence, this cos2 modulation is no longer true because it's just I mean, there are other geometrical effects, and this cross section is mathematically incorrect. So you cannot really fit a two cosine variable. So what you need to do instead is you can just fit with a known template. So you can create different types of templates of these histograms for different polarization angle and polarization fraction, and then just fit that with your data to get the polarization fraction and the angle. And so this is how this is mostly now people have been doing it. Polar One also have done that, and Associated also now in their recent analysis started to use this kind of template fitting. So to do these templates, you also need, of course, you need to simulate all these templates in the to fit the data. So therefore, that what you do is to create a mass model, which is basically geometrical and chemical modeling of the entire detector, and then you simulate all the photon interactions within it. So this is, for example, the model Daksha which I've created, and it's like a single detector simulation, and this is the real CZT detector of Daksha. So we have tried to accurately create this model as accurate as possible, because the scattering and others does affect our systematics when you create the templates, and also when you do the response matrices for spectral and even directional fittings. So this has been used for this polarimetric response and for the results which we have for the sensitivity of polarization. Now the question is that how do you quantify the polarization sensitivity? Because in terms of spectra and all, we just quantify in terms of, let's say, upper limits on the fluence and all. But in terms of polarization, we define something called MDP, which is called minimum detectable polarization. So the definition is that minimum polarization. So MDP is the minimum polarization fraction above which the probability of observed modulation being attained by unpolarized photons by chance is less than %. So in other words, if you were to simplify this, that if you measure a polarization from a source which is above your MDP value, that the polarization fraction you measure has less than 99% chance, only 1% chance to be arising through purely by the noise. So that's just to revert this definition, so that you are sure that this is an order of 3 sigma detection. So you can, for on-axis case, again, you can just invert the probability distribution of this cosine law and get analytical formula. But again, if you go off-axis, because the math doesn't work, so you have to come up with a different way to define to find the MDP. You cannot really use this analytical formula. So that's where we have just slightly different method where we just take the definition and apply use some Monte Carlo to find the MDP. So what we do is that you simulate a large number of unpolarized signal, like 20,000-30,000 simulations of unpolarized signal in your detector, and then you just repeatedly measure the PA and PF on that. That gives you a PF distribution. That's just basically, and then you just take the 99th percentile, just following the definition of MDP. And so that will give you the MDP for that angle or that detector configuration and also. And then you can repeat it, for example, with these different angles, different types of different fluence of the source and other things. So this is what we have done for Daksha. We have made like injected GRBs which are completely unpolarized at different fluence, and then you just measure this PF distribution and compute the MDP. So just to show a quick result about one certain case is that so here what is done is that at a 5-degree incidence we are showing the source of one GRB which is completely unpolarized of fluence 10⁻⁴, and you then just create large number of histograms, like the azimuthal histograms which I showed, and then take the distribution of PA and PF. So here, which is so all the 20,000 points are here, and then if you marginalize over PF and PA, you get a plot, and for in the PF space, you get if you take the 99th percentile, you get an MDP value of 30, which is 0.30 or 30%. That means the minimum detectable polarization for this angle and this fluence is 30. And what is done here is that we have taken 5 faces. So the data from 5 faces is combined here. So like basically top and then the other four faces, they are just arranged a decreasing order of the counts to increase the statistics. And this is just one such fit for one realization of the histogram where we just fit the PA, PF with your templates. So this is basically the final result of the MDP sensitivity is that if you come, like what we do is also, of course, shine it at different angles with respect to the incident lines. That, for example, this was 5 degrees, but we all go all the way up to 90. And what we see is that like there is no angle dependent on the sensitivity for a given fluence, which is a very interesting and important result. So that anywhere in the GRB is coming in the sky, we are more or less uniformly sensitive for a given fluence. And if you translate this plot in numbers, that what means that for a fluence of more than 10 to the power minus 4, so we expect to have a 30% MDP, which means that if GRBs are highly polarized, we can measure polarization of GRBs about at least 5 GRBs per year above this threshold, basically, of the fluence threshold. And of course, if they are if you go lower in fluence, our MDP increases. So if we have even higher polarized GRBs, we can measure the polarization anyway. If it is 80% polarized, lower fluence can be done also. So just a quick test which we did is also to inject GRBs at given polarization angle and polarization degree and then see whether we can recover back. Our analysis is consistent. So yeah, so we injected 2 GRBs which were detected by astrosat and had a secure polarization measurement, and then that's what we got. So we can see the measured and injected values lie very well within the 1 sigma. So to summarize on the GRB polarization aspect, so it is important to measure prompt emission polarimetry to understand the GRB jet and the geometry of GRB jet and the emission mechanism. And we really lack the number of measurements. We have only order of 40 measurements. So we really need to do this expand the field of polarimetry and measure many GRBs, measure the polarization of many GRBs. So the field is looking very promising now. That's in general, the community understand this lack of observation space, or like the gap in the observation space, and there are a lot of missions which are proposed or under consideration. So we of course have Daksha, which is in the proposal phase. There is Polar 2, which is again the successor of Polar, which is being built by ESA and the Chinese space station, on the Chinese space station and the Chinese the space agency. They should go in 2027 or something. There is COSI, which has been also accepted. It should also, I think the timeline is about 2027. Then there is LEAP, which should be going on the ISS. This is under proposal phase, and I think there is a review in February next year about whether it will be accepted or not. So coming back to Daksha, what is our status right now as a mission? So it has been, the good news that been accepted by ISRO for the next phase. So whatever the prototype phase, which like the phase 0 where where they wanted to see the demonstration and all, that has been done and all the reports were submitted. Now ISRO is evaluating the feasibility within the internal team, and then it will go for the funding agency, basically the government, for the approval. So what is shown here just as from some of the calibration run, that this is the one medium energy package PCB. We have 4 detectors mounted on that, and this is the actual spectra which was obtained from the radioactive sources. Our aim was to reach 12% at atom-radium line, and we were able to achieve 10% resolution. So we exceeded the requirement from ISRO. And then also, of course, there are efforts going on the low energy and high energy side also to make the detectors and various aspects of electronics and all. So last line on Daksha is that, like, if you are interested, yes, I mean, we would you can scan the QR code, also follow this and quickly fill this form about what you want to work with Daksha, and the data will be public. So, and we'll also give updates time to time, and this will also help us to show the community interest whenever we have the funding agency reports to be submitted. And also I can share the link later with Alessio, and also you can scan it, and of course follow the social media accounts for the various updates. So before I go to the radio part, there is just one more mission which is coming up, which should be launched in December. Also, I'm part of that. It's called ExpoSat, and it has 2 payloads. One is POLIX and EXPECT. The POLIX will be medium energy polarimeter based on Thomson scattering. It will be able to observe it. It will do observations of X-ray binaries and pulsar, like about I think about 20 source to 40 sources. Yeah, so it's already ready. So this is the flight model. It's sitting in ISRO right now for integration on the satellite, and it should be launched in sometime in December this year. If you are interested, you can try contacting the PI, which is the Biswajit Paul. Okay, so I'll now come to the other part of this electromagnetic spectrum. Yeah. So as I said, like we have to do this to solve the questions of FRB, GRBs, and electron and the EMGW events. We have to also have to go to do the instrumentation on the both part of the spectrum. So in the radio, we are doing trying to develop a new backend on the CHIME telescope, which we call CHIME Slow. And this is a small team within the CHIME collaboration, mainly based in TIFR and 2 people in Toronto. So this is me, Jashree, she's the PI, the PhD student, 1 postdoc, another project student, and Ziggy and Paul were the postdocs in. Now Paul is a professor in York, I think. Yes. So before I go in the details of what we're trying to do, a quick introduction about fast radio bursts. So FRBs are basically similar to GRBs, are short, bright, and energetic pulses of radio waves. And so they are typically characterized by this dispersion sweep. So basically, if you plot the frequency against time, you get because the higher frequency arrive before the lower frequencies, you get this parabolic shape in the domain where this line, like the color, indicates the intensity. And this dispersion sweep, it's proportional to the electron density across the line of sight, which is called the DM, which is the dispersion measure. And so based on this DM of the most FRBs, we know that they are mostly in extragalactic origin. So the DM is very large. So only the galaxy cannot have that much amount of dispersion measure, except for the one FRB which we have detected, which is known to be a magnetard, which is SGR 1935. So currently we have a detection rate of about 2 to 3 FRBs per day. And one of the key fresh question in FRBs is like, what is the exact sources of these, like what is the progenitors of these sources? So like given the time scales, it is now more or less consensus that it's a compact object, most likely a magnetar or basically a neutron star. But there are still theories which are like whether the emission comes close to the neutron star or very far away, or also is it stable, or do FRBs some class of FRB come from the cataclysmic origins like merging neutron stars. And like GRBs, they are also important in terms of studying the IgM or the host or basically the material along the line of sight, because they interact with the material while coming towards. So one of the key telescope right now which have been very successful in detecting FRBs is the CHIME telescope, which stands for Canadian Hydrogen Intensity Mapping Experiment. And so it is a 100 meter long, 20 meter diameter dish. So there are 4 such dishes like shown here. It was originally meant for cosmological studies, but then there was a backend which has been added, and now it has been very successful in detecting FRBs. It has about 200 square degree field of view, and it's a transient telescope. So basically, these dishes look up only the zenith part of the top part of the sky, and the sky rotates along as the Earth moves. So it basically searches for 1 millisecond times resolution, and then in the 200 square of field of view for the FRBs, and it's like it has something called 1024 digitally formed beams, basically small parts of the sky on the horizon which is visible, and then it can localize within those beam the detected event. So this is one typical bright FRB detected by CHIME, and you can see the time series, and this is dispersion corrected. That's why so the sweep which should be there given the DM has been corrected, so the intensity is exactly aligned with the pulse. If you come to look at the transient radio phase space, if you look at the radio or the width of the transients against the luminosity, there is some small gap in the few seconds, few hundreds of milliseconds to few seconds transients. So we have millisecond pulsars, FRBs at a very shorter time scales, and then other radio transients such as GRBs or XRBs, which are at a higher time scales. But there is still an observation gap in this kind of pulse width domain. And over the last 1.5 years or so, we know that there are events which exist in this gap. So there were, for example, 2 detections in 2022 from Meerkat, one from Meerkat and one from MWA. So where Meerkat detected about a second duration pulse, which has a period of 76 seconds. So it was a pulsar-like emission with 76-second period, which they think is to be ultra slow magnetar and ultra long period magnetar. And the MWA detected a similar event where 18 minutes period and about 30 to 60 second pulse width. Even itself, the CHIME detected one event which is about 3 seconds long, and it was able to detect it only because it has substructure. It has substructures in the total pulse period, and so it was able to trigger on the CHIME detection pipeline. However, so we basically need, and then there are theories about, as I said, which are about counterparts to BNS mergers, which could involving at least one neutron star, which could have a precursor radio coherent emission, and those timescales come up to about few hundreds of milliseconds. So, however, the current CHIME sensitivity, purely because of the technical challenges in terms of pipeline and policy decisions, it drops above few tens of milliseconds. So, although CHIME searches for pulses up to about 100 milliseconds, the completeness of the pipeline is pretty low. So that is where we want to improve upon and then fill this gap with this time slow backend. So what we are trying to do is detect transients between about 50 milliseconds to 5 seconds pulse width. And we are piggybacking on the data for another backend which is being developed called CHIME slow pulsar search, which is being used to detect slower duration pulsars. We'll be able to detect, we'll be doing this study over about 1/4 of the sky, which is visible to CHIME, and this will be our largest systematic survey at these time scales. So basically filling this gap in the previous block. So how do we are doing it? So we have a pipeline working now, and the idea here is that not invent something new, but use already known routings. So what we do is take the CHIME FRB data, which then is compressed by 3-bit compression for this CHIME SPS search. Then we basically downsample it to the 3 different time scales, so that it allows us to search for cover the large 50 millisecond to 5 second window. And then we pass it to something we call Presto, which is a well-established pulsar search software, and it also can look for search for single pulse searches. So what it does is that it cleans the RFI based on basic statistics and all. It is and then it de-disperses the signal, because we have to search for large number of dispersion measures. We don't know a priori what is the dispersion measure of the given signal is. Then it just does the single pulse search, which is just a boxcar filtering on the time series. And then it gives you something called DM time and SNR event list, which is basically it shows you what is the DM of the event, what is the time, and what is the SNR of the event in the time series. Then you can apply some kind of event clustering to see how the events are clustered. I'll show a figure in a moment with what I mean by clustering. And then it is passed. Some of the promising candidates are passed to one machine learning tool, which is called Fetch, which has been developed to detect such to basically classify such transients, and it does pretty good job to show whether it is a real transient or just an RFI. In addition, we have also developed injection mechanism, because we are then training the Fetch as well as these parameters to be used for Presto. With these injections, we are injecting events and doing this analysis to fine tune the pipeline. So we have the first version of this ready, and we have tested on some test data right now, where we were able to detect the pulsar with the pipeline. So what is shown here now is, so on the left, just focusing on this graph, is the dispersion measure which we searched for, and the duration of one single file for which we did the search. And you can see one cluster here, which actually belongs to this pulsar at DM of about 140, and the pulse width of about 130 milliseconds or so. So you can see this cluster, there is a cluster of events here. So basically the DM time and SNR of these events is very high in this part of it, because when you do the dispersion, you will also detect a signal which is slightly at offset DMs just because of if it is a bright enough pulsar. And if you pass it through our pipeline, you can detect. And then this is the fetch plot of the pulsar. You see the intensity as a function of time and clearly see the pulses, which is the pulse period is about a second or so. So we are able to detect at least bright pulsars right now, and then we are working on getting onto more data. So right now, we are actually copying over some data which we were obtained in December 2022 and 2023. So the immediate plan for next 1 or 2 months is to do this pilot survey where we will search this data about which is about a month long, which will cover about 12 square degrees in sky. And if the rate is similar, or if the FRB rate is similar to CHIME FRBs, we will be able to detect, like we hope we might be able to detect at least one transient. We are going to go real time. We have funding for that also from the Renlap Institute, and we are in the process of buying the hardware. So once we buy that, we will directly put that hardware on the CHIME site and put the pipeline in a more automated manner to do this search on as and when the data comes. So, and of course, even in this search and in the real-time search, we are planning to follow up the LIGO events as well as the GRBs to see if at all there is any kind of concurrent radio emission following these events. Yeah, and I think that's all I have. So thanks.
Thanks a lot. Thanks for being in time also. So we have time for questions.
Thank you very much. Very nice talk. I have a question on your last topic. So I see you have shown a region in the transient diagram where you will be sensitive. Yes, this region. So in practice, more or less in terms of periods, which is the period range that you will be.
So we are not doing any periodic search. We'll just do the single pulse search. So we are not doing any folding. Okay. So I mean, if it's bright enough, then
let's say 2 pulses distant 3 hours. Are you gonna check it? Which is even
3 hours, probably not, because it will transit out of the field of view. So it will be So we will be sensitive to as long as the pulse, like the source is within if the pulse, okay, if the period is less than the duration of the transit within CHIME.
Okay.
Because otherwise
which is the range of the transit, just to have an idea on how sensitive you are to.
I forgot. I can check the number. I can let you tell you later. I forgot the number. Yeah. Okay. See, because it also has to be in the like on the same beam rows and also and then also if it's going the other way around. So I think it will depend on RA deck and some stuff like that. So it's slightly how the source transits exactly over the horizon.
Yeah.
But if we detect that every day later, you could probably see that's a periodic source. But I mean, like if you are seeing every day, like yeah, I mean, if that source is getting detected every day or 4 minutes earlier or later, you know that it's kind of a periodic, and then maybe you go and do the folding later or something with
the survey that you're looking at, it's the last 1 month, right? You said.
Yeah, that's we don't have the data yet, but we will do. I mean,
and in 1 month, how many times you will pass from the same place in the survey?
No, it's just the sky passes, right? We are not doing any. So the sky is passing. Then I need to compute that. Yeah. So yeah, right now the idea is to get the data.
Don't worry. It's when.
So questions. I have one. Maybe I have one. So going now to Daksha. So you're expecting to measure polarization in GRBs. What about the chances of measuring polarization in other transients, like magnetars?
Yeah, it can.
Like, do you think it will be comparable to X-band, for example, in terms of performance?
Transients, transients, yes. So it will depend highly on the fluence. And this is done in the medium energy range. So then your fluence is 20 to 200 kV. So I suspect that magnetar flares are pretty hard, I think. So there you will get enough fluence. But I think other X-left flare binary flares are pretty like softer, so then it is not, you not get
More
anything.
fun,
Yeah. Magnet are issued, so we wanted to do it, but like for this paper, we focused only on GRBs, but I think at some point we'll find out what can sensitivity be done for typical magnetoflares.
And just to have like an idea of so it's in the proposal phase, you said. Do you know when you will know if it's like accepted?
So optimistic case is that mid next year we go for the funding approval. If it is approved, then we are hoping 3 years to the launch, because there is no technology development much. It's just all the technology is already available. So these detectors for CZTI detectors on the CZTI, so we know, and then the low energy detector also used in the moon mission, and the high energy detectors are also used in some other. Okay, so it's just that getting the funding and putting people and manufacturing the things. So yeah, so 4 years optimistic, but yeah.
About the Daksha proposal, so maybe I didn't get, or maybe I missed it. When you detect the GRB, do you use LU or not?
No, they just open
this is
detect.
an
We just all Sky 2 detectors. So two satellites. So you just localize it. You localize it based on the counts, like, and then you just send an alert immediately. So we will have the onboard trigger to detect this on the onboard, and so then the alert will go in a minute or so to GCN to others.
So you will not be able to keep pointing this.
Yeah, there is no pointing per se, because it's open. There is no coded mask or something, so you cannot really image. The only thing is just the count. Like it's like a GBM does the localization.
Yeah.
Any questions? So online people, can you hear me?
Yes. Yeah. Hi, it's Francesco. Can you hear me?
Yes.
Okay. Thank you for the very nice talk. I also have a question. You showed the slide on the upcoming X-ray polarimetric mission EXPOSAT, and I was wondering if it can actually provide at the same time polarimetric and spectral timing information. And the second question related to this is if you could compare the flux sensitivity with the current XP mission, would you be able to give some estimates and comparison between the two missions?
So first question I didn't understand. What was it?
So the first question is, because I see that the mission will carry 2 instruments.
Yes.
So the question is if they will allow for simultaneous polarimetric and spectral timing measurements.
Yes, so the spectral timing can be done in this low energy with expect. The Polix, which is the main instrument that can only do polarimetry, the spectral resolution is not going to, because we need to integrate over large band, otherwise you'll not have sensitivity enough. So the spectra won't be really, spectroscopy won't be really possible. So you'll have to do simultaneous observations with some other missions which have a good spectra in that range. But at the lower energy, the expect can do. The idea also is because we'll need a lot integration time for Polix, like to do the polarimetry, it will observe about a millisecond, at least a megasecond or something for typical sources. So the expect will point at the same time. So you have a variability of the source in the field of view for about a megasecond in the softer energy range. So you can do the timing for very longer duration. And in terms of XP, so we are in the process of publishing, putting the papers out for this, like final ones with the sensitivity. But I'm not so sure whether it can be compared because the energy range is completely complementary. So it's going to be less sensitive because it's not focusing. That's all that I can say, because it's just a collimator on a scatterer. So the sensitivity is not that great. So we need longer integration times compared to XP. Yeah.
Okay, thank you very much.
Detailed paper should be out in 2 months or so, at least hopefully.
Okay, great. Thank you.
So, maybe save for a final question, if any, or otherwise. I have some speakers. I guess speakers. Some speakers. I keep it here.
Nice.
So if there's another question, I would thank again Sujay. Thank you. I think he will stay in the magnesium room for maybe 30 and on tomorrow. If you like.
No, I think I can be at least an hour for sure.
If you have a follow-up question, you can go to the magnesium room. He will be there. And then tomorrow and the Friday there will be nothing here. So like take advantage of it now because otherwise you can